HR waiting email. So welcome. Can't see. Are there people in the session? Vika, can you admit that? But people are there. Okay, welcome to this live session, the first live session on quantum Hall effect. So you are encouraged to ask questions. I can tell you a little about the course, but it will be better that if you have any question, then on the basis of that, I can elaborate more the idea of this course. And it's certainly not a the first level course of solid state physics. One should know enough about the first course on solid state physics plus quantum mechanics. These are the requirements. You could please ask me questions, and then I'll elaborate on the course if required. Good afternoon, Deepak. Vishan, good afternoon. Becca, am I muted? Am I muted? Yes. Okay, all right. Okay, so just to give you a very brief about the course is, as I said, is a higher level course in condensed matter physics. Quantum Hall effect is one of the benchmark discoveries that have changed the way condensed matter is perceived. So it sort of allowed us to think that there are topological invariants which decide on the Hall conductivity or the plateaus of the Hall conductivity. So these are the things that are have been taught or will be taught, throughout the course, in which you will see that there are many aspects which are very fundamental in nature. In fact, this Hall conductivity or the plateaus in the Hall conductivity is related to a topological invariant, and the whole, the quantum Hall system that really describes a topological insulator. And what I mean by topological insulator is that the bulk of the system is insulating, just like a normal insulator, just like plastic, say, for example. But the edges are conducting. Okay, in a two-dimensional sample, this is what we have shown, that the edges have these conducting channels, which are gapless modes, by which the electrons actually conduct electricity. So it's a very different kind of system. It is no analog in the first solid state course that you have encountered, where you have seen, the band theory of solids, etc. Um, okay, let me come back to your question one by one. Tamanna is asking which level of quantum mechanics will be learning, college level or university level. Quantum mechanics would definitely be at the university level. But yes, I mean, basic concepts of, matrices and writing down wave functions, etc., they are required, which are also taught in the college level. I would say the quantum mechanics may be either college level or university level, but the condensed matter, the solid state physics is definitely university level. Deepak Sai, you're doing a research in theoretical condensed matter. Congratulations on that. I'm facing difficulty, feeling difficult in the field. And this course also, can you suggest how to work in the field and the course also? Okay, so can you elaborate what is your field of research? Now, for this particular course, you follow exactly the lectures, every lecture you try to work out, all the slides would be supplied, you look at the lectures and try to work it out on your own, such that you feel confident that what I did on the board, you are getting that as well. So be with me throughout the course. It'll be very helpful to sort of do it that way. If you can tell me what exactly, what sort of aspect of theoretical condensed matter you do, then I can give you more suggestions. Tamanna, if you want to apply it for a research, yes, you'll be able to do, this course has applications in research such as, say, of course, the quantum Hall effect, then these topological insulators, then this quantum information theory, then there are these spintronics. This course will give you a lot of exposure to all these things. To tell you very frankly, I did not have time to go into a lot of quantum information and quantum computation, but there is another course which is going to come up after this in the next semester, which is on topology and condensed matter physics. That course will have a better view of these things, where I do a number of models, topological models in 1D, which have direct connection with quantum information. So yes, you'll be able to do after this course. Deepak, if you tell me about specific problems, I'll be happy to answer. Raj, Karthik, good evening. So what I mean by the topological insulator is, this is a 2D quantum Hall sample, and you have the bulk of the system is the electrons actually go around like in closed orbits. and these are called cyclotron orbits. So this the bulk is like this, and so on. So there are only edges where the conduction happens. And these are edges where these circles do not get enough space to get, make a full circle, and that's how it's called as topological insulators. So quantum Hall is one of those. Quantum Hall systems is one of those. Yeah, I'm waiting for more questions. Uh, you'll study how to build MRAM by not applying magnetic field in its place. You'd rather use semiconductors or topological insulators that exhibit. Yes, 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 yes. Okay. So I understand that. That is a good this thing. So basically, the magnetic, component. So you'll not employ a magnetic field, but then the spin orbit coupling that acts like a local magnetic field will do a spin selection, and that's exactly what a magnetic field does. But magnetic field, breaks the time reversal symmetry, whereas these spin orbit coupling doesn't break the time reversal symmetry. So you'll have a time reversal symmetric system, and there'll be, the spins will carry the information, and that's a very good field of research. See, Drude theory, Tamanna, is the first, theory in solid state physics, which explained the origin of resistivity. Because if you take a complete, non-interacting model of electrons, then they are only non-interacting and they do not give rise to any resistivity. Now, if you need to get resistivity, what Drude suggested is that let us consider a model which is still non-interacting, but they would only interact and they would, occasionally collide, and then they would go in different. So these two electrons are coming and they're colliding with each other, and they are then, going away in random directions, and these collisions give rise to the resistivity. Now, having said that, between two such collisions, you will have the electrons traversing like free particles. That's which is the basis of free electron theory. So he introduced that these collisions take place after a time tau, which is called as the relaxation time. So it's relaxation time, and this relaxation time is a typical time scale of the problem. And after a relaxation time tau, the two electrons collide and they go in different directions, and then that's how the resistivity or the conductivity comes. The conductivity is not infinite; it is given by some n squared tau over m. Okay, where is the electronic charge? N is the electron density, and m is the mass of the electrons. So so the main one of the assumptions of Drude theory is that the electrons are free, but they collide occasionally, And between two such collisions, they simply, traverse like free particles. The conductivity is given by these ne squared tau by m, or the resistivity is just the opposite of that, inverse of that, not opposite. It's m by ne squared tau, and this is the Drude conductivity of metals, or Drude resistivity of metals. And they also, he also said that, look, I mean, there is also a temperature that plays an important role here. So if there is a hot region inside a metal, then the electrons will be ejected with larger velocity, because the kinetic energy is like half kT types. So half mv square is like half kT. So wherever the T is more, temperature is more, the kinetic energy will be more. And of course, there's another assumption that after the collision, there's no predictability of the direction of the electron. So the velocity after collision is completely random, and you only have them, going in absolutely sort of random directions, so that the average velocity after every collision is zero. So that's that's what Drude theory says. And when you say applications, so basically it sort of tells you about the conductivity or the resistivity of solids. So any metallic system, its resistivity is well explained by this expression, which I just wrote here, m by ne squared tau. You may have to change the m to m star, which is the effective mass of the system. Okay. So applications are in the resistivity of metals. Okay. Yes. The Landau levels are, what happens is that when you take a 2D electron gas, and then you want to understand that what happens. Can I have another slide? The next one. Oh, sure. This one. Okay. Thank you. Thank you. Okay. So what happens is when you have 2D electron gas, then what happens is that you have these density of states that look like this, and so this is the like the density of states E, and this is the DOS, and so on. So in presence of a magnetic field, this constant density of states, it just kind of breaks up into these so these are the Landau levels and so on. So this is E, and this is like half H cross omega B, 3 half H cross omega B, and 5 half H cross omega B. So omega B is equal to EB over M. Okay, so that's how the electrons respond to the magnetic field. So in presence of the magnetic field, if you solve a one particle Schrodinger equation, Schrodinger equation is one particle. So just non-interacting electrons, and you solve Schrodinger equation. So which is like P minus EA divided by, so this is, it has to be P minus QA, so it's a P plus EA whole square over 2M, and psi, this is equal to E psi. This solution, E becomes equal to N plus half H cross omega B, and these are called as a Landau level. So these N equal to 0 is the first Landau level, N equal to 1 is the second Landau level, and so on. Okay, so this and where does this magnetic field enter? The magnetic field enters through this A. That is the potential where B is given by curl of A. So here I've done this in the class that for a given choice of B, that is B is in the perpendicular direction to the plane. So B is in the Z cap direction. So A can be either in the X cap direction or in the Y cap direction or in the combination of X and Y cap direction. So if we take it in any of the direction, this is called gauge freedom. So the gauge freedom is, so you take a particular gauge, we have taken a low range gauge until we come to the, the fractional quantum Hall effect where we have taken a symmetric gauge. You solve this and the Landau level come. Is the reaction of electrons, what does it say? If the is it a reaction of electrons is similar to resonance? No. Reaction is not similar to resonance. A reaction of electrons to magnetic field, no, there's no resonance here, but the electronic, which is, the constant energy, that is, the energy is independent of, or the density of states being independent of energy, which means that any energy, the density of states remain constant. Now, in presence of the magnetic field, there are these discrete Landau levels that are formed. Okay. Deepak, Matsubara frequency is a frequency that comes in the finite temperature Green's function. Okay, so if you're doing a finite temperature field theory, then the usual Green's functions are replaced by Matsubara Green's functions, and the poles of those Green's functions give you Matsubara frequencies. Okay, and these Matsubara frequencies, there can be, these bosonic Matsubara frequencies or fermionic Matsubara frequencies, which are these omega Matsubara, let's call it as some omega n. So these are either n plus 1 pi over beta or n pi over beta. Okay, let me write as 2n plus 1 and 2n pi over beta. This is for the bosons and this is for the fermions. So what you have is that the Green's function will have branch cuts at these frequencies. That's called as a Matsubara frequency. How particles can go in higher stage. Oh, they are all available energy levels of the problem, Tamanna. They are all available energy levels that now you start, suppose you have these Landau levels. I think you're talking about Landau levels. So these are the Landau levels, and these are available for occupation. And like infinite number of electrons can occupy an energy level. Okay. So this is very different, than usual your Pauli exclusion principle. Exclusion principle says that no two electrons having the same quantum number can occupy. But here, of course, you are allowed to occupy in any number of electrons, infinite number of electrons in this. So electrons only will go to the next Landau level if you change the magnetic field. because these difference between two successive Landau levels depends on the magnetic field. Okay, so if you change the magnetic field, so these are like E as a function of so these are some I mean, so these n equal to 0, n equal to 1, n equal to 2, and so on, and you're plotting it E as a function of B. So then, these are constant Landau levels. Okay. Yes, good question. I mean, this is what I was going to tell you, but then I jumped over to another question. Deepak, there's imaginary frequency. The Matsubara frequencies are imaginary frequency. You have to understand that what happens is that you have an exponential I omega t as the temperature, the time variation for any quantum system, right? But the temperature variation is like exponential minus beta h. All right. So you see there's a I here and there's a beta here. So in order to keep it at the same footing, what you do is that you interpret temperature as the imaginary, or rather, here you take imaginary time, or you make the frequency to be imaginary, such that these two are put on the same footing, so that we a temperature variation and a time variation, they look similar. That's how the Matsubara formalism has been, developed. I'm happy that you're asking this question, but this course has got nothing to do with Matsubara frequency. We haven't done any finite temperature calculation. There is another course of mine called Advanced Condensed Matter Physics. You'll see that there is a lot of discussion about Matsubara frequencies. Yes, thank you, Deepak. Please ask more questions. And the frequencies are these Matsubara frequencies are imaginary frequencies. That's how I said that there are, branch cuts in the complex plane. So, I mean, you ask this question, what is the physical significance of Matsubara frequencies? They give you the poles, that's the excitation energies at finite temperature of a system. So these are like n equal to 1, 2, 3, etc., which are odd multiples of pi over beta, where beta is the temperature, 1 over kT. So that tells you that these are the energies of the system, all the energies, including, all the excitation energies of a given many body system. So that's the utility of this Matsubara-Green's function. Exam questions will be like if you follow the classes, the class notes, materials, it will be completely from there. Because it's a higher level course, we wanted to make the exam or the evaluation to be easy. So if you follow everything and do it yourself, everything will be very easy. In fact, easier than most of the exams that you have written. Can you explain in topological insulator why topology? That's the reason that we were talking about. I mean, this first thing. If you look at the top, this figure, which I said is the topological insulator, because the topology means, the word topology means that it is integration of certain geometric quantities. Okay, so that's what topology means. So here, most of the time, we talk about topology as integration of the Gaussian curvature. Okay, so if you get a thing like this, like a, what do you call this? I mean, it's something like this. There are in the sitting room, you have such things for sitting on the. So it's like a seater. If you have this and you want to calculate the Gaussian, the total Gaussian curvature, that's that is integration over the curvature of this entire thing, then this has a particular value which is given by the Gauss-Bonnet theorem, which tells you that this curvature, integral of the curvature, so let's call it as a 1 over r, and then over the entire surface is a constant. And this constant actually counts the number of genus. So the topology is coming because we are talking about smoothly deforming something. Like the example that was shown in the class about which everybody shows is all over the net, that a mug becoming a donut, it has the same number of folds under a smooth transformation. So you don't spoil the system, you don't break the system, you don't puncture the system. So that's why it's called so there is a topological invariant, and in the insulator, the bulk of the insulator, that is the inside the material, it is insulating, that is, it doesn't conduct, but at the edges it conducts, and that's why it's called a topological insulator. The topology is coming because you are distinguishing between different parts of the system. Like here, we just talk about in this seater, we simply just talk about the outside surface being integrated over. Or if you try to deform this thing, so that's why it's called topology. The connection to topology comes. Apprenticeship research in a well-known university, you have to just so it's like internship. Internship, you should apply for some internship program, or you write to professors that whether they have funding to have you for internship so that you can learn and so on. And a lot of internships are available both in India and abroad. People want for small time, engagements from both from uh, the the faculty side and the student side. So it's a good idea. A lot of such positions are there. Sometimes they pay, sometimes they don't. But if you can arrange for a paid internship, that's very good. There are advertisements, like for example, this France, Germany, they have these paid internships. A lot of students go. Qualification is, your master's degree would be good enough. Sometimes bachelor's degree are good enough. There's no, one way or the other. It just depends on the requirement of the person who would be hiring you for the internship. Grading system of colleges, most often it affects the application, but people also understand that sometimes the bookish knowledge is not the only thing that you should acquire. Maybe you are very good in hands and so on. Very recently, you can see yesterday's news all over. There is somebody called Sampriti who did not do so well in her exams back in India, and then she wrote for internships and so on. And then she got an internship, and she lives in San Francisco Bay Area, and she's made a flying, boat, a boat that doesn't. It sort of floats on the this thing and on the water, not on floats on the water. It's above the water, and that has been a very successful mode of transportation and green transportation. So these are some of the success stories of people, even without doing very well in studies, have gone and reached really very big, good places. I mean, studies means she must be really good, but that how good is she, etc., is not the measure is not only the marks and grades, probably more than that. But yes, when you apply it is it is seen that how good are you and so on. Deepak, theoretical condensed matter, I mean, there's nothing called good India or abroad. There are best places everywhere. Okay. Overall, because you are comparing India with probably at least 30 other countries where reasonably good physics is done. So of course I would say that abroad, because it's just 30:1 a number of institutes, etc. But India is also doing pretty well in terms of a lot of research papers, patents coming up, a lot of new ideas being floated. Yeah. So there's no definitive answer for that. Both are good. Uh, as I said, that if it's the comparison is India versus the rest of the world, then I would say rest of the world, because there are so many institutes in the rest of the world which India alone cannot compete. Exam questions I've already discussed. There'll be simple questions, subjective type, where you have to work out things. It is not going to be objective alone, but there could be objective questions and subjective. But you have to work out things. There'll be no knowledge-based questions most of the time. I have a senior apply for an internship in France, but grading system requires different grades that he has taken. Oh, yeah, of course. This is that whole thing about this. I know that. So there are equivalents of grades. So you have taken a 4-credit course, and 4 credit means what? In IIT, it's a 4-credit course may mean an 8-credit course somewhere else, or a 16-credit course somewhere else. So whether this course grades, I mean, what do you call the number of points? How are they transformed? That's a thing. I mean, most of the time, your university or institute gives you a certificate saying that this means this. That is like 40 lectures have been conducted, and there are 2 exams, one at the middle, one at the end, and so on and so forth. So there is no the ministry. I don't know whether the ministry does issues. In IITs, we issue those certificates. Despite having 96 point, he turned down this thing. How can I avoid this? I have no answer to this question. It's not related to the course. Please ask questions which are related to the course. More questions, please. Thank you. Please type your questions. We have, 45 minutes already has been gone. Some questions maybe from you? Uh, well, I have to wind up, but I'll wait for 5 more minutes if there are questions. Otherwise, I'll assume that you're done with your questions. You only have a few minutes to go. So what I can say about this is that it is definitely a higher level course, but then you should also understand that there are these courses that lead to research and so there are usually no courses before you start your PhD. This is one of the courses that are designed that you find it comfortable to start your PhD. Um, and by giving examples, I've done things quite rigorously. I've given you um, that hand holding which is required for solving things. We've done many things. I mean, anomalous quantum Hall effect, spin Hall effect, normal quantum Hall effect, BHZ model, etc. Many things that have been done which are required for one to understand the material properties. And if you're going into theoretical condensed matter physics, either India or abroad, this is one of the main things that you have to learn. Of course, one can also do completely numerical or computational work, which a lot of people do, such as the DFT density functional theory and so on. But on the other hand, these are the quantum condensed matter, and a lot of things can be actually done analytically. I have shown how to calculate the Chern number and from the Berry curvature, Berry connection, and so on and so forth. So many of the things that are usually not taught in courses such as even a condensed matter 2 course, which probably deals with interacting systems and magnetism and superconductivity and things like that. This is unlike that there are necessarily you have to invoke interaction. Excepting for fractional quantum Hall effect, you didn't have to invoke interaction at any place. Even there, the interaction, taking into account the interaction is difficult because you have to do a completely numerical exact diagonalization study for a number of electrons. Now that is cannot be done in a course. So this part is what I can tell you. Okay. So I guess there are no questions. No more questions. We have nearly 55 minutes have passed by. If you have questions, you could ask the TAs or you can mail me directly if you have any difficulties. I'll be there to answer. For now, then we are, switching off. Okay. In just a moment, we'll switch off and wish you all the very best for the rest of the course. And there's an 8-week course, so there'll be one more meeting of this kind. So please gather all your doubts by then, and so that you can ask me, and not only ask about how the exam should be and so on. Ask me details about the course. I'll be more than happy to answer. Okay. All right then.